In this video, we're going to use the node voltage method to find the voltage VO, which is the voltage across this 1K resistor. Now, because we're going to use the node voltage method, we should know by now the very first thing we must do is identify all of our essential nodes and take one of those essential nodes to be our ground node. So I'm just going to call this node 1, and we want the voltage at node 1. This is going to be our second essential node. I'm going to put V2 because you want the voltage at node 2. And this is going to be our third essential node. And we have one more essential node at the bottom here. And I'm just going to take this as our ground node. So I'm just going to draw the symbol right here. Now that I have this, I'm going to start to find the node voltages at each node. So I'm going to start at node 1. So I'm going to have node voltage at node 1. Okay, so we're going to assume the current is leaving this node, going in this direction here, this direction here, and this direction here. Okay, so for the current coming downwards in this branch, we're going to have V1 over this 1K resistor. So we have V1 over 1000 plus, we're going to take the current now going in this direction here. We're going to have V1 minus V2 over 2000 plus, we're going to have the current flowing in this direction. Well, wait a minute. When we look at this branch, we see we don't have any resistor, but we have a voltage source that's going to be between two essential nodes. Now, anytime we have this, the first thing we want to do is to try to identify if we know the voltage at any of those essential nodes that the voltage source is going to be between. Well, we don't know the voltage at node 1. And for the voltage at node 3, we don't know this voltage as well. Therefore, this is going to form a supernode. So at this point right here, we actually have a supernode. So we're going to ignore this 12 volt source for now. And we're just going to start writing KCL equations for the current at node 3. We're going to assume the current is leaving this node. Okay, so instead of it being node voltage at node 1, I'm just going to write it as node voltage at node 1 and node 3. Okay, so this is just a super node. Now let's continue, right? So we're going to have V3 minus V2 divided by 1000 for the current in this branch. So you have V3 minus V2 divided by 1000 plus we have V3 divided by 1000, and that's going to give us the current in this branch. You have V3 divided by 1000, and that's going to equal 0. Now let's simplify this. The LCD out of these terms is going to be 2000. So when we multiply each term by 2000, that's going to leave us with 2V1 plus V1 minus V2 plus 2V3 minus 2V2 plus 2V3, and that equals 0. And we start to simplify this now. Okay, so when we simplify this, we're going to get 3V1 minus 3V2 plus 4V3, and all of that equals 0. So this is going to be equation 1. This is equation 1 for us, right? Now we know we're going to have a constraint equation, so let's write that down. We have a constraint equation because of that supernode. And because we have the polarity of the voltage source to be positive to negative, and because we know the positive terminal is closer to node 1, that means that the voltage at node 1 is going to have a higher potential than the voltage at node 3 because of the polarity of this voltage source. Therefore, we're going to say V1 is the higher potential, so we're going to say V1, which is the voltage at node 1, minus the voltage at node 3, and that's going to equal 12 volts. So we're going to have V1 minus V3 equals 12 volts. Okay? And this is going to be equation 2. Now let's do the node voltage at node 2. So let's write that down. We have the node voltage at node 2. And when we start to do this, right away we should be able to identify something. We have a sole voltage source that's going to be between node 2 and the ground node, which means node 2 is just going to equal the value of that voltage source. Now, because of the polarity of this particular voltage source, we know the value of V2 is going to be a negative 6 volts because the negative terminal is closer to node 2. Therefore, we know V2 equals negative 6 volts. So this is going to be our answer for the voltage at node 2. Now what we can do is we can just plug this in to this equation up here, and let's simplify this equation some more, right? So we have 3V1, let me just bring this down. So we have 3V1 minus 3. Now we know V2 is going to be negative 6 volts because of the polarity of this voltage source. So we're going to have negative 6 plus 4V3 equals 0. When we solve for this, we're going to get 3V1 plus 4V3 equals negative 18. So this is going to be our updated equation 1. Okay? Now when we look at this, we have two equations. So we have two equations and we have two unknowns. So we can just use simultaneous equations, or you can use the matrix method. I'm just going to use the matrix method. So I'm going to have a 2 by 2 matrix, which is going to be 3 and positive 4. We know the unknowns is going to be V1 and V3. And that's going to equal negative 18 for equation 1. And for equation 2, we're going to have a positive 1 and a negative 1, and that's going to equal positive 12. Okay, so when you put this in our calculators, we're going to say the inverse of A multiplied by B. When we do that, that's going to give us V1 equals 4.29 volts. And V3 equals negative 7.71 volts. Okay? So these are the voltages at node 1 and at node 3. Now the problem says, find the voltage VO, which is the voltage across this 1K resistor. And we know the voltage across this 1K resistor is going to be the same voltage at node 3. Therefore, we can say that V3 equals VO. Therefore, VO equals negative 7.71 volts. So this is going to be our answer for this particular problem. VO equals negative 7.71 volts.